In this video, we're going to talk about vector spaces. Let V be a set on which two operations, vector addition and scalar multiplication, are defined. Then we say that set V is a vector space if the following conditions are satisfied. First, let's talk about the conditions we need to satisfy for vector addition. The closure property. If vectors u and v are any vectors belonging to vector space V, then u plus v belongs to V, the vector space. The commutative property, which says that for all vectors u and v in V, u plus v is equal to v plus u. The additive identity property. The set V contains the additive identity element 0, where for any vector V in vector space V, 0 plus V equals V, and V plus 0 equals V. The associative property. For all vectors u, v, and w in vector space V, u plus v plus w in parentheses is equal to u plus v in parentheses plus w. The additive inverse. For every vector v in vector space V, v plus x equals 0 and x plus v equals 0 contain a solution x in vector space V, which is denoted by negative v. Now let's look at the properties for scalar multiplication. The closure property states that if V is any vector in vector space V and C is any real number, then C times V is in vector space V. Next is the distributive property, which states that for any real number C and all vectors u and v in vector space V, C times u plus v is equal to C times u plus C times v. Number 3, the distributive property again. This time, for any real numbers C, D, and all vectors v in vector space V, C plus D times v is equal to C times v plus D times v. The associative property, which states for any real numbers C and D and all vectors v in vector space V, C times D times v in parentheses is equal to C times D in parentheses times v. And finally, the scalar identity, which states for all vectors v in vector space V, 1 times v is equal to v. It's important to consider the fact that a vector space is made up of 4 elements: a set of vectors, a set of scalars, and the 2 operations, vector addition and scalar multiplication. When considering a vector space V, all 4 of those elements should be clearly stated or understood. Unless told otherwise, assuming the set of scalars is the set of real numbers. Next, I'm going to list a few common vector spaces. R2, with its standard operations, is a vector space. Another vector space is Rn, with the standard operations. Also, let me back up to R2 before we write this one. I'm just going to write the form of R2. I'm going to take the form of V equals V1, V2. Okay, So Rn, with the standard operations, is also a vector space, where V equals V1, V2, V3, Vn. The set of all 2 by 3 matrices with operations of matrix addition and scalar multiplication is also a vector space. And they take the form another vector space is the set of all polynomials of degree 2 or less. For example, P2 would be expressed as P of x equals a sub 2 times x squared plus a sub 1, a scalar, times x, a variable, plus a sub 0, a constant. Another vector space is the set of continuous functions. Contained in this set are all polynomial functions and other continuous functions on the entire line of real numbers. F of x equals sine of x, for example, would be included in this set. G of x equals e to the x would also be a member of the set of continuous functions. Now let's look at a couple of examples of sets that are not vector spaces. The set of integers is not a vector space. One example of why is suppose we have an integer 1. Or actually, let's make the integer 3. So if we have an integer 3, and we multiply 3 by a scalar, 1/2 times 3, the result, 3/2, is not an integer. In other words, it is not closed under multiplication. Another set that is not a vector space is the set of second-degree polynomials. So in other words, if we have p of x equal to x squared, and q of x equal to negative x squared plus x plus 1, we can see that this would not be closed under addition, since we'd have x squared plus negative x squared plus x plus 1, which equals x plus 1, a first-degree polynomial. Let's go back for a minute to the vector space, the set of all polynomials of degree 2 or less. Notice that we can state this is a vector space because if we were to have the example that we just used for the set of all second-degree polynomials, we can see that the second-degree polynomials would have been added and become a first-degree polynomial, and would still have remained valid under the set of all polynomials of degree 2 or less. So note that subtle distinction. Anyway, we can continue to find examples of vector spaces and sets that are not vector spaces. But for now, we'll conclude this example. I hope you found it helpful, and we'll see you next time.